Hello everyone, welcome to our differential equation class. In this video we are going to apply the linearization analysis we introduced in a previous video to continue our study of the competing species system. So in this video in particular we are going to review the linearization analysis. Then we are going to introduce the competing species for both infinite and finite food resources, and then we are going to solve a couple of examples that have a different description of what happens in the system. In one example we are going to see that the system predicts the extinction of one of the species, and in the other example the system predicts the coexistence of both species. So that's the plan for today. Let's start reviewing the linearization analysis we introduced in a previous video. Recall the linearization analysis works for autonomous systems, systems of this form, linear or nonlinear, where the right-hand side of the equation does not depend on the independent variable time, for example, explicitly, only through the function of the equation. So we write the equation in vector form like this, and recall this is a vector with two components, two functions, f1 and f2 of the variable x or of the system. So what is the linearization analysis? Well, the first step in the linearization analysis is to find equilibrium solutions, which are also called critical points, which are constant solutions of these equations, of this system of equations. So constant solution means this derivative equals 0. So we are looking, and we are using a different notation here, we are looking for constant solutions of the equation, so solution of this equation, this side of the equation equals 0. So there could be multiple solutions, equilibrium solutions, and the next step is to find what is called the derivative matrix, also called the Jacobian of the system, which is constructed with the right-hand side of the equation. Recall the right-hand side of the equation is a vector value function with two components, and the components depend on the variables x1 and x2. Here we are using the convention, I didn't say it, but at some point we should say that x is actually a vector or a point with two components, x1 and x2, and using this notation, then this is how we construct the derivative matrix. We grab each component of the right-hand side of the equation, of the vector field that defines the equation. This is the first component, this is the second, and in the first line in the first row of the matrix, derivative matrix, we compute the derivative, and this is incorrect, the derivative with respect to x1 here, and of the function f1, the derivative with respect to x2 of the function s1, and in the second row we do the same but with a second function of the equation. So the derivative matrix is simple to compute. You have the two functions that define the equation. In the first row you use the first function, the top function, and you compute the derivative with respect to x1 and x2. In the second row you grab the second function that defines the equation, and again compute the derivatives with respect to x1 and x2. And you get a matrix that is a function of x. So this is not a constant matrix. In general, this is a matrix valued function. The next step is to evaluate this derivative matrix at each of the critical points or equilibrium solutions that we found in this step. So if we found 3 equilibrium solutions, then we evaluate the derivative metric at 3 points, and we are going to have 3 of these matrices, and these are now, so this we do that for each equilibrium solutions, and now these are constant matrices. So with these constant matrices we solve for each one of them, we solve the corresponding linear system u prime equal that matrix here, times u. Recall, this is now a constant. This here is a constant matrix. And now we have, if we have 3 equilibrium solutions, we have 3 linear systems to solve, for example. And now we use the eigenvalues and eigenvectors of this matrix for each, again, for each equilibrium solution. We use the eigenvalues and eigenvectors of the derivative matrix at the critical points to characterize this the solution vector u, the solutions u for each equilibrium solution. And by characterize, we mean we want to know if the phase portrait of the solutions of this linear system correspond to a source, for example, source node or spiral, sink, source or spiral, saddles, nodes, or centers. Could be any of these possibilities. And then we try to relate what happens to the solution of the linear system to what happens to the solution of the nonlinear system. We try to relate these two things. So we have computed the solution of the linear system for each critical point, and that is going to give us, sometimes, is going to give us information about the solution of the nonlinear system. And the relation is given by this result, which is called the Hartman-Grobman theorem, that says that the behavior of the solutions of the linear systems, so these are the linearizations of the nonlinear system at each equilibrium solution, the solution of the linearizations is similar to the solution of the nonlinear system near, and here I have the wrong notation, near the equilibrium solutions we found for each equilibrium solution. But this relation holds for sources, sinks, and saddles. Sources, it doesn't matter if it's a spiral or a node. It doesn't matter if the sink is a spiral or a node. This relation holds for all these cases. But the only case that we don't know what happens is when we have a center, that we need to do further study to relate these two behaviors. Sometimes for centers, the behavior of the linearization is similar to the behavior of the solution of the nonlinear system, and sometimes it's not. So we need to do further study for centers. For these other cases, the behavior is similar. So once we know that, we use all that information, we use all the above, and then we need to add some more information that usually comes from the direction field that is defined by the right hand side of the equation. We put all that together and some information from the direction fields to sketch the phase portrait of the solution of the nonlinear system. The solution here. The phase portrait, we should say here, of the nonlinear system. Of the nonlinear system. And this is in one page the linearization method. Now let's use this linearization analysis to study the solutions of the competing species system. In a previous video, we have already studied the case of the competing species with infinite food resources, which is given by this system of nonlinear equations. Recall the variable x1 measures the population of one of the species, let's say rabbits, and x2 measures the population as function of time of the other species, let's say sheep, and they are competing, these two species, for the same food resources, but the food resources are infinite. So we introduced this system of equations in the previous video. Recall that the infinite food part of the system is given by this part of the equation. When we don't have sheep, for example, then this term is not there, and this equation is not there. And then what we have is the exponential growth equation for the rabbits, the population of rabbits, and this reflects the fact that we have infinite food resources for the rabbits. Something similar happens for the other species when the rabbits are not present, and that's why this model described population model with infinite food resources, and the competing part is because we add these two terms that slow down the rate of change of both populations due to the competition between the two species for the same food resources with different coefficients here, alpha 1 and alpha 2. Recall the coefficients in the equations are R1, which is positive, R2 are positive, which are the birth rates of each population. Then we have the coefficients alpha, which are also positive, which are called the interaction coefficients. And these coefficients alpha quantify how each species affects the other species. And these are these terms here. That the result of the competition is to slow down the rate of change of the other species. We use already the linearization analysis on this system in a previous video, and this is the conclusion we obtain. We obtain that the phase portrait of solution of this system, a sketch of this phase portrait looks like this. We haven't solved anything exactly, but this is how the solution must behave. And we have two equilibrium solutions, one here, one there. So if you put initial data right here, the solution stays there, and the same here. If you put initial data over here, what the phase diagram says is that the population is going to move in this direction. And what is going to happen is the population of x2 is sheep, is going to go to 0, and the population of x1, which is rabbit, is going to go to infinity. So the population of rabbits is going to survive, the population of sheep is going to go extinct. If you have initial data here, so more sheep at the beginning, what is going to happen is something like this. And then we see that the population of rabbit is going to go to 0, and the population of sheep is going to go to infinity. So in this case, the population of sheep is going to survive, and rabbits go extinct. So essentially, any initial data on this region, only the x survives, the x2 survives, so sheep, and on initial data on this region, only x1, which is rabbit, survives. And if we have population along this line, then they are going to coexist, but this has no physical meaning because this is the same situation when you have, for example, a stick that is standing, a very thin stick that is standing, and yes, there is one position where suppose there is a pencil that has a sharp end, and the pencil is standing vertically. Yes, we have this solution that mathematically is there, but physically it's never, we can never do it because nothing is perfect. We can never put the pencil exactly vertical, and what happens is the pencil goes one way or the other in real life. And this is the same type of situation with this line of initial data. You can never have your physical initial data exactly on that line, so it's either on one side of the line or on the other. So this system predicts that depending on what is your initial data, this model predicts that one of the species is going to go extinct, and the other species, the population, is going to go to infinity. So this is the result of the linearization analysis for the competing species with infinite food resources. And now, in this video, we are going to focus on the competing species with finite food resources. Again, we have x1 and x2, which are the populations of rabbit and sheep. And what is the main difference with the other equation? Let's put both equations together. So this term is this term, that term is that term, no change here. If you multiply out, then this term are these two terms, so this is exactly the same system, plus the addition of this term that is actually proportional to x1 squared, with a negative sign and some coefficient. And if you multiply here, we have another term that is proportional to the population x2 square with a negative term and some coefficients. So the only difference is, let's zoom in, is these terms here. Recall, these are the terms from the logistic equation which, when we don't have, suppose we don't have ship here. So this term is going to be 0, this is going to be 0, and the whole equation here is going to be 0. And what we have here for the population of rabbit is now the logistic equation, which is an equation we studied in the previous video that models populations with finite food resources, and the solutions, recall, are something, either are two equilibrium solutions, and then the solutions have an S form, or they are like this. And this is time, and this is x1, when x1 is alone. So this is the logistic equation, which we know pretty well how the solutions behave. When there are only sheep and no rabbits, the first equation disappears, this term disappears, and we have a logistic equation for the sheep. So same behavior. And now we have the interaction. So this is the model we want to study. The new constants we have introduced here, we already know from a previous video, K1 and K2 are carrying capacities. And these constants quantify how many individuals can be sustained by the finite food resources available. So this is the system we want to study, the competing species with finite food resources. Okay, let's study the competing species system with finite food resources, but instead of doing it in general, let's fix a particular competing species system where we give some particular values to all the coefficients, and we change the names. One of the species is going to be the function r of t, the population of rabbits, and the other s of t, the population of sheep. Rabbit and sheep. And well, this system is called extinction for a reason that we are going to see at the end of the calculations. So let's solve this system solution. So let's use the linearization method. What is the first step in this linearization method is to find the equilibrium solutions. Okay, so this is the same as critical points. So critical points. These are constant solution of the equation. So if we look for constant solutions, this is going to be 0, this is going to be 0, and here are the equations we have. What we are going to do is, you see this factor r multiplies this term, and we have another factor r here, so we're going to pull these two common factors. And also this 3, we are going to distribute it here, so to make the calculation a little bit easier. So we are going to end up, if we do that, with r common factor. Recall, the 3 goes inside in these two terms. The 3 does not multiply the last term, does not. So then we are going to have a 3 minus r, and then minus 2. Recall, the r is common factor, s equals 0. So we have that equation. We do something similar on the second equation. We distribute the 2, and the s, with this s, we pull it common factor. So we are going to have s, wrong color. We are going to have s multiplying 2 minus s minus, recall the s is outside, r equals 0. Okay, what this says? It's nice to have the equation written as a product of two factors, because when it's equal 0, that means one factor or the other has to be 0 to find solutions. For example, one solution is this r is equal 0, s is equal 0, r equals 0 satisfies the first equation, s equals 0 satisfies the second. So we have r equals 0 and s equals 0 is one solution. Then another solution is r equals 0. So we have this solution satisfied. And then because r is 0, it's not there. And then we can have s equal 2. And then we are going to satisfy the second equation. So r equals 0 and s equal 2. You see, this is because we wrote the equation in a nice form as a product. Then it's easy to see the solutions. Then another solution is we can play the game on the other side. S equals 0, and because s is 0 in the so that satisfies this equation. S equals 0 on the second means that another solution is r equal 3. So r equal 3 and s equals 0. We have already 3 solutions. And now what is the other possibility? The other possibility is that this is 0 and this is 0. Okay, let's write down these two equations. So or the other possibilities, let's do it here. Or we have 3 minus r minus 2s is equal 0, and 2 minus s minus r equals 0. Okay, so you can check if you do a little bit of algebra, you can check that the solutions is r equal 1 and s equal 1. And it's easy to verify that this is the case. You put 1 and 1, you have 3 minus 3, 0. You put 1 and 1, 2 minus 2, 0. So this has to be the solution. Okay. Then all that implies that we got four equilibrium solutions, which are, let's put them here. x0, the first one is 0, 0. Oh, how we are gonna name the variables? So what about if when we have an ordered pair? So let's call the ordered pair first rabbits and then sheep. When we have x1 and x2, it's easy that, well, x1 is the first and x2 is the second. This is our convention. But when we call them r and s, which one is? Well, we need to say which one is. So r first, so rabbit first, sheep later. Using that convention, then what is the other equilibrium solution? Now is important. Now is r equals 0 and sheep is equal to. The other equilibrium solution is equilibrium solution 2 is r is equal 3 and sheep is equal 0, and the last equilibrium solution is 1 and 1. Well, all this is the conclusion of our analysis here. And we can draw them, but I already did, and is here. These are the 4 solutions. So here, with this convention, in the this is the phase space, the variable space, r and s, rabbit and sheep. The first variable is the variable that we draw on the horizontal axis, and we said is rabbit. This is the variable for the vertical axis, sheep. And then we have 0, 0 is this point. We have 0, 2 is that, 0, 3 and 1, 1. These are the 4 equilibrium solutions. Okay, so now what is the next step? The next step, and let's put it maybe here, is to compute the derivative matrix. Okay, the derivative matrix, recall our conventions. If we write the equation in vector form as x prime equal some vector field function of the point x, and this vector field has components f1 and f2, and recall we are using now the vector form of the variable, which is rabbit first and sheep later, which agrees with the point version here. If we do all that, then the derivative matrix, so let's put it here, the derivative matrix function of the point is going to be equal. And now what is the best way to write the components of the equation? Well, this way has products, which is not good for derivatives. So what I'm going to do now is I'm going to distribute the terms R on all three terms, the term S on all three terms, because now I'm going to have a polynomial which is easier to compute derivatives. So, for example, let's keep that on site. We are going to have the derivative R of 3R minus R squared minus 2RS. Then we need to compute the derivative with respect to S of the same thing, 3R minus R squared minus 2RS. This is a 2 here. And now the other equation, again, recall, I'm going to distribute the factor, and we are going to have, what we are going to have? The derivative with respect to R of 2S minus S squared minus RS. And now the same function, derivative with respect to S, 2S minus S squared minus RS. So that is going to be our derivative matrix. And if we do the calculation of the partial derivatives, recall partial derivative is a derivative with respect to this variable if we keep the other constant, and this is the result. If we do the partial derivatives, we get, what do we get? We get a 3, we get minus 2R minus derivative with respect to R, so it's 2S. Here the derivative with respect to S kills all those terms, and we have only, what do we have? Negative 2R. Now here the derivative with respect to R kills these two terms, and is only, we have only negative S. And in the last component, derivative with respect to S, so we have 2 minus 2S minus R. And here is the derivative matrix. Okay, let's put some parentheses here to indicate that this is the whole component. And now, what do we need to do? Now we need to evaluate the derivative matrix, which is a function of the point, at each critical point, at each equilibrium solution. Which, recall, we have named them x0, x1, x2, and x3. Okay, so we can do it slowly, but here is the result, and you can check whether this is correct or not, but it should, hopefully is correct. The derivative at the point 0, 0, this is easy to see, that we are going to get a 3, then a 0, then a 0, and then a 2. Okay, what is the other one? The other one is the derivative matrix at the point, well, let's emphasize which point we are working here. So we try to be as clear as possible. This is the derivative matrix at 0, 0. Okay, at 0, 0, this is what we get. Now the derivative matrix at the point 1, at the point x1, which is the derivative matrix at, where did we say it is? 0, 2. 0, 2. And what we are going to get, if you do the calculation, you get here negative 1, 0, negative 2, negative 2. So check that this is the case. Then the derivative matrix at the point x2, which, if we recall, is the derivative matrix at the point 3, 0. And we should get something of the form negative 3, -6, -1, and 0. Evaluate, again, what we are doing is evaluating this matrix at all these points. And we have the most complicated of all the critical points, which is the derivative matrix at the point x3, which is the derivative matrix at the point 1, 1. And that is gonna, if we do the calculation, we should get -1 and -2, -1, -1. Okay, that is what we get when we do the 4 linearizations, the 4 derivative matrix at each critical point. So now we need to solve linear systems. So now the next step is more or less here. Solve the linear systems What linear systems? Well, the linear system let's use u prime function of t equal these derivative matrices at the critical points x critical, let's say, times u, ugly u, times u, for each critical point xc, I call it, which is any of the x0, x1, x2, and x3. Okay, so let's start with the solution for the first critical point. So we need to solve the linear system u prime equal the matrix 3, 2. So it's 3, 0, 0, 2, acting on the vector u. Well, this is the very simple system because it has eigenvalues. The eigenvalues here are lambda plus equal 3, the larger eigenvalue, and lambda minus equal 2. Both are positive. And what are the eigenvectors? I don't want to write this all over again, so I'm gonna copy and we are gonna use it later. So, well, the eigenvector, the v plus, is easy to see from the matrix. That is obviously the eigenvector 1, 0, and v minus, we don't need to do all the calculation, is obviously the 0, 1. And what we see here is that the solution u equals 0 is actually, because both eigenvalues are positive, is a source. Is a source node. And then the phase diagram should look like something like this. So we have the eigenvalue v plus, that is not good. The eigenvalue v plus is this one, the eigenvalue v minus is there, and then is a fork, recall, going in the direction of the larger eigenvalue, is a source node. Good. So that's one, 3 more to go. Let's go to maybe here. Here is good. 2. Now we need to solve the linear system u prime equal with the second matrix. The second matrix has a -1, 0, -2, -2. If I remember correctly, times u. Let's check. Yeah, is this matrix here. Okay, that is the linear system we need to solve now. Well, we need to do a little bit of work, but for the eigenvectors. So what do we need to do? And here is where I'm gonna use it. We need to write the eigenvalues and the eigenvectors for this matrix. The eigenvalues are pretty easy to find because they are the diagonal elements of the matrix, because this is a matrix that is upper triangular because of this 0. You can compute the eigenvalues if you want by analytically with the determinant of matrix minus lambda identity, but the result is gonna be that lambda plus is the largest eigenvalue is the least negative, -1, and lambda minus is -2. And then what are the eigenvectors? Well, that is requires some work, so let's put here some work. But the result is going to be that lambda plus is 1, -2. This is one possible eigenvector, and the other, v minus, is going to be, well, this is easy to see, is 0, 1. So now the solution u equals 0, the origin is now a sinc node. And then this is how it looks like. Notice that one eigenvector, the v minus, is 0, 1, so it's this vertical vector, and this vector is 1 in the horizontal component, 2 in the negative vertical, so it has to be a vector like this. So it's kind of a weird looking sinc. Alright, that's that. 2 more to go. Number 3. Number 3 is we need to study the solutions of the linear system with the other matrix that is -3, -6, 0, -1, acting on the vector u. Okay, again, we need to find the eigenvalues and eigenvectors for this matrix to find what the solutions look like. But as before, this is in this case, upper triangular matrix. So these are the eigenvalues. So lambda plus is going to be the least negative, so -1 in this case. Lambda minus is going to be the other eigenvalue, -3. And then with a little bit of work, we can get the eigenvectors. And v plus here is going to be, if you do some work, it's going to be -3, 1, and v minus is going to be 1, 0. That is easy to check. So what happens with the solution u equals 0 in this case? Well, the trivial solution is now one more time a sinc node, because both eigenvalues are negative. But it looks a little bit different from the other sinc node because the eigenvectors are different. So now v minus is horizontal and v plus is this weird 1 up vertical, 3 negative, so it's even more slanted than this one. So that is how this sinc node looks like. And then the very last one. The very last case is, so let's put it here, case 4. We need to study the solutions of the linear system u prime equal, and this is a complicated matrix, -1, -2, -1, -1, acting on the vector u. Alright, so now we really need to do some work to discover that the following are the eigenvalues and the eigenvectors. The eigenvalues are going to be lambda plus, the larger eigenvalue is going to be -1 plus square root of 2, which by the way is positive. Then lambda minus is going to be -1 minus square root of 2, which by the way is negative. So we already know that we are dealing with a saddle node, and the eigenvectors are a little bit hard to find, nothing terrible, but we end up with negative square root of 2, 1, so very close to negative 1, 1, a little bit slanted. And then V minus, if you do the calculation, you're going to get that this is square root of 2, 1. Also slanted, but in the direction close to 1, 1. So, what is this, the equilibrium solution u equals 0 in this case? Well, it's a saddle node. And this is how it looks like. The vectors are a little bit slanted, so not exactly 1, 1 or negative 1, 1 because of these constants, these components. But this is this direction is the solution with negative eigenvalue. In the other solution is the direction with positive eigenvalue, and then we have the typical saddle shape. So now, with all these 4 linearizations, we use neither of those is a center, which is good news. So now we can use the Hartman-Grobman theorem on each of these linearization, and the behavior of these solutions of the linearization is similar to the behavior of the solution of the nonlinear system near the critical point. So how do we use this result? Well, this result says the following. If we go to the phase space of the nonlinear system, so now we have sheep and rabbits. Before we had U1 and U2 in all these pictures, because we are studying linearization, so linear systems. Now we are back to the nonlinear system, and we have recalled the 4 critical points. But now we know that this critical point here is a source node, because this is what we obtain up here, source node. And the other 2 on the axis are sinks. So this is a sink, this one is a sink, and with the weird direction given by the eigenvectors. Recall the eigenvectors we computed, and we are focusing only on this region because these are population. We are not interested in what happened here. We could, but it's more work and we don't have much time to do it. And recall, this critical point is a saddle, so maybe we can even do some little pictures like this. So this is the behavior of the solution of the nonlinear system. Is similar to the behavior of the linearization near the critical points. The solutions of the nonlinear system here behave like a saddle, here behave like a sink, and here they behave like a source. So now what we want to do, and this is what Hartman-Grobman theorem says, and that's all we can get so far. Now, how we can get from this picture to a global picture of what happens here, 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 and here, and somewhere here, and somewhere there, and over there. Well, if we use a little bit more information from direction fields, for example, the direction fields along this axis, they are pointing this direction, and here they point in that direction. Here the direction field points up. It's just evaluating the right hand side of the equation, and you can see that this is the direction of the direction fields. With that information and putting everything together, we obtain the following phase portrait for the whole system. We still have, let's make it a little bit simpler, we still have this information here, but now we use that the direction fields here are horizontal, going out or going in, so the solutions have to be like that, so no crossing solutions anywhere, the same here and the same there. So, and here we have a saddle, so the solutions have to behave in this way. So this is the phase portrait of the solution of the nonlinear system given by the competing species with finite food resources with the numbers that we put in our example. All this is heavily, this is the one particular competing species system with the coefficients given by the numbers we chose in the example. So one last comment on this picture before we move on. This model also predicts that one species go extinct, because what happens if we give initial data here? The solution goes to that critical point, which means that the sheep go to 0, and but the rabbits don't go to infinity, go to that point. And if we start here, the solution is going to go there. So sheep is going to be different from 0, but rabbit is going to be 0. So this model, like in the previous competing species model, it predicts that one species always go extinct. And if you have initial data anywhere on this region, then the rabbits survive, but with finite population, doesn't go to infinity because the food is finite. If you have initial data here, the sheep survive with finite population, and the rabbit goes to 0. And if you have initial data on this line, then it goes here and both species coexist. But again, this is not physically happening because it's an unstable situation, like the pencil standing on a table. So physical systems are going to behave either with initial data like this or like that. So physically, this model predicts that one species goes extinct. So this is how we can use the linearization model to see what the competing species solutions looks like for this particular set of coefficient values. What happens if we choose different values for the coefficients in the competing species system? For example, suppose we choose these values now, which you can see they are different from the previous example. Well, we may get a different result, as we mentioned here, coexistence. What that means? Well, we need to do the linearization analysis for this system, which, as you saw, is pretty long. So I'm going to show you the steps, and then you can verify this calculation. So if you do the linearization analysis, you start computing the equilibrium solutions. If you do it for this system, you're going to get again 4 points, like before. Then you need to do the derivative matrix and the linearizations on each of these critical points. Okay, here is the result. First linearization is going to be derivative matrix at 0, 0. Second linearization is going to be derivative matrix at that equilibrium solution, some coefficients. If you study the solutions, you're going to see this is a source node, just like before. But now this is a saddle. Recall in the previous example, we got what we got? We got a sink here. Now it's a saddle for these coefficients numbers. So the behavior of the linearization depends on what numbers do you have here. So now it's a saddle. At the other equilibrium solution, 1, 0, in this case, you get another saddle. And then in the middle, this is the complicated case. Recall, this is the complicated critical point. Well, you are going to get the complicated matrix with eigenvalues. You can check that these are the eigenvalues, but both are negative now. Before we had one negative, one positive. Now both are negative, and now this is a sink. And these are saddles. Before it was the other way around. These were sinks, this was saddle. Okay. So if you put all that information together and you do the analysis with direction fields on the axis, now you get this picture. Now you have a saddle here. You see, these are the directions going toward the solution, and this direction goes away from the solution. So saddle. Also saddle here with weird eigenvectors. This direction here, you see, depend on the coefficient of the matrix. We need to compute it to do the picture. Here we still have a source, and now here is a sink node. And you see, no matter where you give initial conditions, well, it matters. So as long as the initial conditions is not on the axis, so if the initial condition for both species is different from 0. So if you are here, then it doesn't matter where you start, you end up always on the same spot when t goes to infinity, which is here, with both species having non-zero values. So this phase space diagram predicts that this model predicts the coexistence of rabbits and sheep. So it's a very different prediction from the previous system. So depending what the coefficients are, the competing species system with finite food resources predict two different outcomes. That depends on the coefficient of your system. Either you get extinction, which means one of the species goes to 0, or you obtain coexistence, where no matter where you start, as long as both initial data are different from 0, you end up here. Both species coexisted with finite populations. The different outcome depends on the coefficient of the system. In the textbook, we are going to do a more general analysis, and we are going to decide why we have this behavior, and actually it has to do with obviously with the values of the coefficients, and all that is going to be explained in the textbook. But here in our video, we are happy that to show you that we have two different behaviors for the solutions of the competing species system with finite food resources, and the behavior depends on the equation coefficients. Okay, that's it for today. See you guys in the next video.